Hello everyone and welcome to the channel. Now in this particular video we are going to take questions from Organic Spectroscopy portion of your CSIR-NET exam which happened all India on 15th of December. Now if you have not watched previous videos where we have solved already questions which have been asked in your physical chemistry portion, 2 marker and 4 marker both, and also in organic portion in the 2 marker in the all India level and also in the Assam and Meghalaya region exam. So I will recommend you to watch those videos as well. I will be attaching that video within this I button, so you can just click over there and watch that video later on. So in this video I'll be taking questions which were asked in your CSIR-NET December 2019 exam on 15th of December, right? And these questions are from organic spectroscopy. So I'll try to explain you. There are not much questions. There were 5 questions from organic spectroscopy and they were very good questions. They need a proper explanation to be done. So let's start with it. So the first question over here, you can see it says that the structure of the compound which displays the following spectral data. Now the IR data is given to you at 1690 centimeter inverse and 1100 centimeter inverse. Proton NMR has 1, 2, 3 and 4 peaks you are getting in proton NMR, and in the carbon NMR you are getting 1, 2, 3, 4, 5, 6 and 7 peaks in the carbon 13 NMR. So first of all let's talk about IR, okay, because IR is going to help you to find out the functional group, right? Now if you can see there are 2 peaks which you are getting in the IR band, and these 2 peaks basically is like it's going to tell you that there are actually 2 functional groups which are there in the molecule. Generally we get 2 peaks for the ester group, right? Because there are two types of stretching which is happening. One is carbonyl stretching and the other one is CO stretching. But for the ester the range is like, for ester you know that for esters your IR range is more than your 1750, right? Around 1750 centimeter inverse. Okay, so that's for your esters, right? So this is for your carbonyl stretching, and the other stretching which is CO stretching, okay, that is C single bond stretching, not double bond. So C single bond stretching is around 1100 centimeter inverse. So that means this particular IR is obviously not going to be about the ester group, right? So you can just cancel out those options which have ester in them. So this option 1 can be cancelled out and option 2 can be cancelled out. Now you are left out with option 3 and option 4, right? Now since this 1690 is basically 1690 centimeter inverse is actually for the ketone only. So it's telling you that you have a carbonyl, you have a ketone, like they are basically talking about the carbonyl of the ketone group. And 1690 centimeter inverse, it is quite lower than the usual trend which is 1700 or 1710 because of the like conjugation of that ketonic group. If you can see in both these options, in 3 and 4 both, you will get a conjugated ketone, right? Here also and in this case as well. So that means what? That the IR data is correct according to option number 3 and 4. So now much you cannot do in option 3 and 4, like not much you can do from the IR basically. And the other one is CO stretching. So here is your CO bond, here is also your CO bond. So basically your CO bond stretching is there. So that's why you are getting this 1100 centimeter inverse. So you got both the values and they are satisfying both the things. This is for the ketone, this particular one, whereas 1100 is for the C single bond O stretching. Talking about the proton NMR, now how to identify these two, that is going to be done through your proton NMR, okay? So in the proton NMR, if you see, there are just 1, 2, 3 and 4 peaks. There are just 4 peaks which you are getting. If you look upon option 3 and 4, if you just count the number of peaks which you will get, the number of signals which you will get, or how many different types of proton you have in this series. So we'll do it like this, that you have A type of proton, which will be the methyl protons. You will be having B and B type of proton, both will be equivalent and they will be aromatic protons. This will be C and C type of proton, again aromatic but different than B1. And then you have D type of proton. So you got 4 types of proton in option number C. In option number D, if you see, so how many protons you have? So you will have one A type of proton, which will be methyl proton. Then you have B type of proton. It is not equivalent to this, so that's why it will be just B. This will be C type of proton. It will not be equivalent to this. It will be D, it will be E. All these 1, 2, 3, 4 protons will be different because of different chemical environments, and this will be F. So basically 6 peaks you should get over here, So that's why and in the question you are just getting 4 peaks. So that is clearly telling you that option C should be correct. One more thing is which is satisfying, or which is just telling you, or which is just confirming that option C is correct, is the coupling. So remember always that whenever you have doublet and J is equals to 8 hertz coupling, okay, and because of 2 hydrogen, if it is given for 2 data, okay, if this thing is given for 2 data, it means that there is a coupling happening between like it's happening between two of the carbons, the two adjacent carbon, and basically both of them contain two hydrogen. So that means basically they are talking about this group, this hydrogen and this hydrogen, and this hydrogen and this hydrogen. So the coupling of these carbons with with these particular carbons. So that's what it is mentioned. So it is always telling you that it is a para substituted group. Okay, so para substitution. So para substitution is being observed in this. So para substitution is only in option C. So correct option becomes your option number 3. So that's how you can easily go with the options, and that's how you can answer it. So two things are very important to be known. First is IER data. You should be very good at finding out that which IER peak is going to tell you about which functional group. And second is your Proton Nmr, where you should be able to identify that how you are interpreting the couplings and how you are trying to find out. Now if I just want to tell you the values, so how it is going to happen. So if you have this particular molecule, let's say so in the same molecule I'll show you that what chemical shift will be according to which methyl group. So now you have 3 hydrogen singlet and 3 hydrogen singlet. This is higher, okay, the methyl group, like this chemical shift is higher for this methyl group, which is 3.8. So obviously this is for your OMe group, okay. So this will be 3.8 singlet and 3 hydrogen. That's what you will get for this, so because of this hydrogen, okay. So let me just write down the chemical shift value, that's it. So this you will get at 3.8, and this one, this methyl group, you will get at 2.8, okay. So that will be the chemical shift values of both these methyl groups. Now talking about the protons, so these 2 protons and these 2 protons. So if you look upon them, so if you look upon the oxygen over here, so oxygen is going to give you the resonance effect over here, so that electron density on this particular carbon will increase, and since the electron density on this carbon will increase, this proton becomes shielded, and because it is shielded, this will become little upfield. Now due to that upfield, the chemical shift of that is going to decrease a little bit, right? So you will have 6.9, so you will get 6.9 because of this, and you will get 7.8 because of this, okay. So that's how we have interpreted all the chemical shifts of the particular molecule, and the correct answer is your option number 3. Now let's go to the next question then. Alright, so in this particular question, it says that the compound that shows peak in EI mass spectrum at M by Z of 121, 105, 77 and 44. Now whenever you are getting this kind of question, first of all you have to look upon the options, okay. Just look upon the options and see that whether in any option, because mass spectrum is very prominent with your effect which is done over here, that is called as McLafferty effect. So you just have to look upon the options that whether McLafferty effect is happening in any of one of them or not. Or one more way to approach this question is to go with the smallest one, okay, the smallest M by Z value, that you are getting at 44. Now 44, how you will get? So there are 3 things which can happen in the products. If you see, so there can be a fragmentation of this NH2 group, or it can be a fragmentation of CHO group, CHO group. Then there can be a fragmentation of CONH2 group. There can be a fragmentation of NCH3 group, okay, these are methyl groups, or it can be a fragmentation of NHCOH group, okay. So let's see that what does that, like which of them will have that. So if you just talk about NH2, so the mass of this is mass of nitrogen is 14, so overall it will be 16. Talking about your CHO, the mass of carbon is 12, hydrogen will be 1, and the oxygen will be 16. So if you add all of them, so you are going to get 29, right? So that's what you will get, right? So 29 is what you will get. So you are not getting any peak at 16 or 29. So first option you can just cancel out, okay. So that is not going to be the correct option. Now let's talk about CONH2. So CONH2, let's talk about this group, whether we are getting this or not. So the carbon is going to give you 12, oxygen is going to give you 16, nitrogen 14, and plus 2. If you add all of these, basically you are going to get 44. So this 44 basically is because of this CONH2 group. Now this CONH2 you will get in the option number 2 also and option number 4 also. Okay, in 2 and 4 both, because if you count this is also CONH2 only. Alright, that's good. And if you talk about option number 3, so that is also not going to be the one, because if you just look upon the fragmentation like this, so how much mass it should give you? So 14 because of nitrogen, and carbon 12, and this is 15. So 15 plus 15 is 30. So overall again you will get 44. Okay, so here also you are getting 44 in this case. Alright, so that's done. That 44 you are getting either in option number 2 or in option number 3. Now the next thing is 77. Okay, so 77 is obviously is going to be the mass of your the mass of your phenyl group. Okay, so the mass of your phenyl group is going to be 77. So this is going to give you 77 mass. Talking about 105. So for 105, if this phenyl group is attached with a carbonyl group, okay. So if this is the phenyl group and if it is attached with the carbonyl group, in that particular case you are going to get how much? See, 77 because of this, and the carbonyl group, carbon is going to give you 12 and this oxygen is going to give you 16. Alright, so if you add all of them you will get 105. This is the only way how you are going to get this. In the case of option number 3, the fragmentation can be at most like this. Okay, so that means you have this phenyl group, and along with that you have nitrogen, and along with that you have CH3. So if you add them, so you are getting 77 plus you will get 14, and plus here you will get 15. Okay, so if you add them, obviously you are not going to get 105, right? So the value will be around 106, which is not a peak over here. So that means this option now you can cancel out based upon this peak. Okay, based upon this peak you can cancel out option number 3. So either option 2 is correct or option 4 is correct. Now among 2 and 4 also you just got to know that whenever this phenyl ring is attached with carbonyl, then only you are going to get 105. So that means in this case you are not going to get that with the phenyl ring along with nitrogen and hydrogen. You are not going to get that. Okay, you can check it out yourself, that if you have phenyl ring along with NH, so how much you are getting? So 77 plus 14 plus 1 is 15. So obviously it's very low than that. So 77 and plus 15 is going to give me 92. So which is not any peak in the molecule, right? So that means what? That option number D is also wrong. So it's the mass spectrometry is based upon a lot of hit and trial method, where you have to see the fragments. You have to see for the first timers it's not that easy. You have to just keep on checking all of them. For a one person who has already practiced questions on mass spectrometry, he will automatically get to know the mass of NH2 group, the mass of CONH2 group. So these things are automatically in his mind. Mass of methyl group. So these things will be already in his mind. So he does not have to do that much of paperwork to solve them, the way I have explained. So that much explanation or that much time will not be invested in doing this question. It will be done very quickly. Okay. Alright, let's go to the next question then. Okay, let's talk about this particular question. It says that for the complex shown below, in the non-fluxional state, the expected phosphorus where it is proton decoupled NMR resonance. Okay, so remember it's proton decoupled NMR spectrum. That means we are not considering the coupling caused by the protons to the phosphorus. Okay, now if you look upon the molecule over here, you have iridium as the complex. That the structure is quite similar to your trigonal bipyramidal geometry, and here you will see that you have a phosphorus here and a phosphorus here. Okay, these are the only two phosphorus which you have. Now first thing is to find out that whether these two phosphorus are equivalent or not. Okay, so first thing is to find out that whether these two phosphorus are equivalent or not. So obviously they are not equivalent. This phosphorus is on the equatorial side, which is this particular phosphorus is trans to this COPH group. So obviously it's non-equivalent phosphorus. Okay, so these are non-equivalent phosphorus. Now if you look upon the splitting pattern of it, you just have to use 2Ni plus 1 formula. Okay, so who is going to split first? So iridium being a NMR inactive complex or NMR inactive molecule, since we are just doing the NMR of 31p NMR, so we just have to look upon phosphorus over here. So two types of phosphorus, how many lines we are going to get? So basically this will be done it like this. Okay, so number of lines will be done in this way, 2Ni A plus 1, this is because of A type of phosphorus. Okay, and multiplied by 2Nib and plus 1, that means B type of phosphorus. You can just substitute the values. So 2 into, you just have 1 of phosphorus of A type and half is the I value given to you in the question already, and here you have 2 into N value is your 1, and it's also given half and plus 1. So if you solve this, you are getting what? You are getting 2 into 2, that means you are getting 4 lines, or you can say that you are getting 2 doublets. Okay, a doublet because of this and a doublet because of this. Now try to understand this, that how the peak is going to represent. So talking about the spectrum, how the spectrum is going to look exactly, so we'll consider phosphorus A first of all. So this phosphorus A will get split because of phosphorus B, because this is just 2 bonds away from each other. So this will be J2 coupling which is going to happen. Now in how many lines this A is going to split? So obviously it is going to split into 2 lines. Okay, so A is going to split into 2 lines, and similarly your B is going to split into 2 lines. So both of them will be separated. Okay, the shift of because of A will be, you will get that somewhere over here like a doublet, and because of B you are going to get a doublet like this. Okay, now both of them will have different chemical shifts value, and that is because both of them have different chemical environment. Okay, so somewhere it will be A and the other place it will be B. We will not go into the exact chemical shift values in that, because that is not being asked in the question and we don't have to do that much detailed part of it. Okay, so just the thing is that both of them will have different chemical shifts, and both of them are going to give you doublets. Overall lines will be 4, 1 2 3 4 lines basically, but what you have to see is that you are getting doublet and doublet, so 2 doublets is what you are getting. So the answer will be option number 4. Let's go to the next question then. Alright, so let's talk about this question over here. It says that in a IR spectrum recorded neat, a compound shows a strong and a broad band at 3300 centimeter inverse. The band becomes sharp and shifts to 3600 centimeter inverse when the spectrum is recorded in CCl4 at high dilution. Now this proves that the compound has what? Okay, now those who have studied IR spectrum, those who have already done questions on this, or those who have studied this concept in detail, they might know that a very prominent signal when you record IR of a particular compound which contains hydroxyl group is at 3300. Okay, so you get broad band at 3300 centimeter inverse, and this shows that the compound has a hydroxyl group, OH group. Okay, now I will show you some IR data and I'll just try to explain you with that. Okay, now if you look upon this data over here, these are 2 IR bands and of the same molecule. It's of the naphthol, 2-naphthol or beta naphthol. So you can see both of them are over here. Now this is recorded in KBr as a solvent, and here it is recorded in CCl4, that is in a non-polar solvent. So when you are doing that in a polar solvent, remember you are doing over here in the polar solvent, you are getting a broad peak at 3500 to 33, or like this particular one is around 3300. Okay, so 3300 centimeter inverse, you are getting that in the polar solvent. And when you are taking a non-polar solvent, in that particular case the peak also shifts, it shifts to 3600, and also it becomes sharp. So the way how the peak is looking, that also changes, and also the value of the shift, like value of the value where it is going to appear, that also changes. Okay, so both the things changes, the wave number also changes and the shape of the band also changes. Now that's because of what? Now here is some points which I have just taken out just to explain you this. So the OH bond of a hydrogen bonded OH is easier to stretch, and it therefore absorbs at lower wavelength, lower wave number, and this is because of your Hooke's law. This is very simple thing, that a hydrogen of OH which is hydrogen bonded to the other OH will be easier to stretch. Okay, you can easily stretch that. Now there are 3-4 types of OH which are been discussed over here. Let's say I have a non-hydrogen bonded OH, okay, and I should have a dilute solution of that in a non-polar solvent. If I will have a dilute solution, so obviously like the intramolecular or the intermolecular hydrogen bonding will be less over there. Okay, so that's why we have taken dilute solution. So there you will get a sharp peak, and at 3650 or 3590 centimeters inverse, so that's the range of it. Now let's say I have a hydrogen bonded OH group, and we are taking in the concentrated solution. Now we are allowing it to make intermolecular hydrogen bonding. So in that case we'll get a broad peak, and we'll get it at around 3300 or 3500 centimeter inverse. Now if the hydrogen bonded is between the same molecule, if the hydrogen bonding is between the same molecule, that means in the form of dimer, if the dimerization happens, which you will see generally in the carbonyl molecules, okay, in the carboxylic acid. So in the carboxylic acids you will find out that this dimerization happens, and here since you have more number of hydrogen bonding, so obviously the band will be much lower than 3300, and it will be more broad. Okay, it will be very broad. So remember the extent of hydrogen bonding. Okay, more hydrogen bonding means more. What does it means? It means more broad band. Okay, more broad band, and where you will get at lower wave numbers. Okay, so you'll get it at lower wave numbers. Now hydrogen bonded OH stretches at much broader because the hydrogen bonds vary in the strength. Okay, so that's because the strength varies. Hydrogen bonded like hydrogen bonded OH bond will have a variable strength, so that's why it gives a broad band, because you cannot stretch that at a particular wave number. Okay, so you will not have to apply a particular energy to stretch that. You will have to apply a variable energy. You can just understand it in a way that this is just like a plastic. Okay, you, in order to melt it or in order to break this bond, you have to melt it up to a longer range of temperature, whereas this is like a crystal where a particular fix energy is required in order to stretch this bond. Okay, because it's non-hydrogen bonded, so that's why it gives you sharp peak and they gives you broad peaks. Okay, and the higher and lower values are because of the Hooke's law. So that's how this question has to be done. All right, I guess you guys understood it now. Now let's get back to the question, where it was given that the same condition it is given that you were having a broad band, but the band became sharp and it shifts to a higher value when you are recording it in high dilution. That means you are diluting it. So that means what you are removing now. So obviously the molecule will have OH group, and you are removing the intermolecular hydrogen bonding which was earlier. So earlier we were having intermolecular hydrogen bonding, and now the intermolecular hydrogen bonding has been removed. So the answer will be option number 2. Okay, so you have introduced non-polar solvent, and also you have diluted the solution in order to remove intermolecular hydrogen bonding. So this is how this question has to be done, and option number 2 will be your correct option. Now let's go to the next question. Now here the question says that the correct match of carbon 13 NMR is chemical shift of pyridine is. Now this is the pyridine molecule given to you, and they're asking that which is going to be the correct structure of or correct chemical shift of the carbons. Now to answer this particular question, you should know about the resonance structure. You should know that how we can draw the resonance structure of pyridine molecule. So let's try to do that. So let's draw the pyridine first of all. So I have my pyridine molecule like this. Now first thing is what it is going to undergo a resonance. Okay, and nitrogen being more electronegative, the electrons will be pulled towards it, and this is the most stable resonance structure, first most stable resonance structure which you will get. A resonance structure over here, you will get negative charge on this nitrogen, a positive charge on this carbon, and these bonds will remain as it is. Now in the same way these bonds will now rotate, and the next structure you will get here. So you will get something like this. So you will get a pi bond here, a pi bond here, a negative charge on nitrogen, and a positive charge over here. Now again, if you look upon the next resonance structure, this pi electron will shift on that side, and I guess this is not needed to be explained, but yet those who have just forgot this concept, or just for the sake of revision, it's important. Okay, so you'll get a positive charge here, negative charge here, and at the end what is going to happen, that this negative charge will come and you will get the resonance structure of your pyridine at the end. Okay, so here we go. Yeah, so here we got the structure of it. Now if you look upon this resonance structure, you will find out that you will get a positive charge. We are getting a positive charge. If you compare this, so we are getting a positive charge on carbon number 2 and on carbon number 4 and also on this one, but that's not mentioned. But yeah, if you do the numbering, this will also be carbon number 2. So these are the three positions where we are getting the positive charge on the carbon. You can see easily from the resonance structures, right? Now that clearly tells us that the carbon number 2 and carbon number 4 are being electron deficient, and these particular ones are de-shielded. Okay, so if there is less electron density on a particular carbon, they are actually de-shielded, right? So that means C2 and C4 are de-shielded carbons. And remember, whenever you are calculating NMR and in the form of chemical shift, so if a particular group or a particular proton or carbon, anything which is de-shielded means it is going to give you the chemical shift downfield. Okay, downfield means what? Means higher chemical shift value. Okay, higher delta value. So that means a de-shielded group is going to give you a higher chemical shift value. So that means what? That C2 and C4 will have higher chemical shift value. Now among both of them, which is going to give you more higher value? Okay, which one, C4 or C2? So to understand that, we have to look upon the electronegative group. So in a pyridine, the nitrogen is more electronegative, and it is very close to the carbon number 2, right? It is very close to that. So because of that, it is going to make this carbon number 2 more de-shielded. Okay, remember, the carbon number 2 is more de-shielded compared to your carbon number 4. So if I just write down the order of de-shielded carbons, so the order will be like this, that C2 will be most de-shielded, then comes your C4, and the least de-shielded will be C3, because it does not have any positive charge. Now de-shielded means downfield. That means if I write down the order of like the order of chemical shift, so how I will write down that the one which is most de-shielded will have highest delta, right? So C2 will have highest delta, then your C4, and the least delta value will be for C3. So in the same way, you can just go for the options and you can just check out. So if you look upon, so option number 3 is the one where C2 is highest in the chemical shift, then your C4, and C3 is lowest in that. So option 3 becomes your correct answer. So it is very simple to approach NMR questions like this. I hope you guys understood it, and I have made several videos on NMR spectroscopy which are there on my YouTube channel. I'll be giving you link of all those over here in the I button. You can just click on them, you can watch them. It's going to be super fun. You will understand the concept. Once you understand a concept, you can do all the questions based upon that. Alright, so I hope you guys enjoyed this particular video. If you like this video, give it a like, share this with your friends. If you want to ask anything, you can ask me that in the comment section below. One more thing, that if you are new to this channel, do subscribe to the channel. Your one subscription gives me more motivation to make more and more videos for you guys. And that's all for this particular video, guys. Thank you so much for watching, and I just hope that you like this video. You found all these concepts, all these points informative, and that's all. Stay safe and take care of yourself. Bye.